Right. So good morning, everyone. We are recording now. So let's continue from where we left yesterday. So we ended with this question, right? Which is how do you find upper bounds for the maximum value of a flow? In particular, if you can find good upper bounds, then you might be able to convince someone that a certain flow is a maximum flow, right? Um, all right, so let's talk about this. And for those of you who have seen flows before, it's probably going to be a bit repetitive. But at the same time, it's not possible to really skip this part if you want to talk about flows. All right, so let me just provide some intuition without making it formal. You see, an ST flow, so you're sending flow from a vertex S to a vertex T, right? It's some sort of a generalization of paths, actually. You can actually make this more formal, but I don't know if you'll have the time to make it more formal. Right? So in some sense, a flow can be thought of as a generalization of paths um, or dipaths if you're looking at directed graphs. And we have seen that paths are related to cuts. In the same spirit, flows are related to cuts as well. And that's what we are going to discuss today. How are flows related to cuts? Okay. So ST flows are some sort of generalization of ST paths, or if you like, in directed graphs, it would be dipaths. And we have seen in this course that paths are related to cuts. In the same spirit, ST flows are related to ST cuts. But because these are cuts in directed graphs, to be very precise, I should call them dicuts. But in the literature, they are just called cuts because you're already working with directed graphs. So you just call them cuts. All right. So we need to know what an ST die cut is. I haven't defined that yet. So let me just put it in double quotes. All right. Okay. So let's just go through some basic definitions and notation that we'll require for our discussion. So let's say you have a HSTC, which is your max flow instance. Right now, I don't really need the capacities, but I'll keep them anyways. So what is a die cut? It's similar to a cut, except that now we have direction, so we need to be careful as to which edges we are referring to. Okay. So let's say this is a partition of the vertex set U and U bar. Okay. And such that the vertex S is in the U part and the vertex T is in the complement. Okay. All right, so we have two kinds of edges, those going from left to right and those going from right to left. We are going to distinguish between these two. So these edges, we are going to refer to them as partial plus of U. Okay, the outgoing edges. And these edges, we're going to refer to them as partial minus of U. Okay? It's the same way that we defined partial plus for a single vertex and partial minus for a single vertex. All right. So partial plus of u is the set of arcs with tail in u and head in u bar, and partial minus of u is similar thing with head in u and tail in u bar. All right. And by an ST die cut, we mean partial plus of u where S belongs to u. Okay. So, okay. All right. Of course, notice that partial minus of u is the same as partial plus of u bar. Right. Okay. Good. Are there any questions or concerns at this point? All right. So, given an ST die cut, we'll define its capacity. It's going to be simply the sum of the capacities of all the arcs that belong to this cut, to this die cut. Right? So this is going to be simply look at all the arcs in this die cut and take the capacities of those arcs. Okay. All right. So turns out this is the upper bound we are looking for. And before I state it formally, I just want you to think of it in a more sort of physical sense. Right? Supposing you have some sort of a tube network. And you're trying to send flow from the source here. So let's say and let's make it bigger again. Right? Let's say you're trying to literally flow water from S to T. Right? Well, intuitively it is fairly clear, and I'm sure you can talk to a physicist to make these things formal, is that if you have some bottleneck like this, you won't be able to send flow. Basically, your flow, the amount of flow you can send will be constrained by this bottleneck, right? So there is a bottleneck here as well, but notice that as per my drawing, this bottleneck is somehow more constricted than the previous bottleneck. And that is exactly what the MaxFlowMinCut theorem says, that well, that's a theorem, but before that, what we are just saying is the upper bound. So the amount of flow you can send is upper bounded by the bottlenecks that you have in your network, right? And those bottlenecks are precisely your ST cuts. So if the capacity of a certain ST cut is too small, then you can't send a flow that is greater than that. Okay, so hopefully the physical intuition is clear, and I'm pretty sure this physics phenomenon can also be explained through MaxFlowMinCut, except that you may have to take physical considerations into account. Okay. But anyways, this is not a class on physics, so let's go back to mathematics. All right, so it turns out that for any ST flow X and any ST die cut, partial plus u, the flow value which we wrote as fxs is at most the capacity of this cut. Okay, and we will prove this. Okay, so that's the next goal. So let me turn to a new page. All right. Yes. Okay, I'm gonna write bigger. Thanks. Okay, so the proposition is, let's say you are given a max flow instance and x is any st flow and partial plus of u is any st cut. Right? Yeah. So in fact, I'm going to state a proposition that we will use to prove what we want to prove, right? And let's just remember what we want to prove in the end is the following. Okay, this is our final goal. That will turn out to be a corollary of this proposition. So we will prove that the flow at S, maybe I should show a figure to explain this. Okay, so in some sense, this is the value of the flow, right? This is how we define the value of flow X. All right, so just to give you a pictorial sense of what we are about to prove, so what is fxs? It is a sum of the x values on all these arcs which are outgoing from S minus the sum of the values of all arcs which are incoming to S. Right? In general, we may have such arcs. So that is how we defined fxs. What we want to show is that the flow at S, which is this quantity, is the same as the flow for any ST cut. So instead of summing for the arcs at S, I will look at any ST cut and I will add up all the values on these arcs and subtract all the values on these arcs. And turns out that this quantity will be the same as this quantity. Okay, so to put it formally, using a notation which I should define, so let's say x is any function on the edges of your digraph. We'll take non-negative functions because we don't care about the others. And if D is any subset of the edge set or the arc set, then by xd, what we mean is the sum of all the arcs and their x values. Right? Okay, and that is the notation I'm using here. Notice that this is a set of arcs which are all of these arcs. So we are adding up all of these guys, and this quantity we are subtracting from the total. So we are subtracting all of these guys. Okay, so that is what this right hand side is referring to. All right. Okay. I should make one point here. The capacities are actually irrelevant. The only thing we really need is the conservation constraints. We won't need the capacities in any real sense, right? Okay. So the capacities are irrelevant for the proof. We need the conservation constraints. Okay. All right. Before we prove this statement, let us see why this implies the main thing we want to prove, which is that the value of any flow is upper bounded by the capacity of any cut. Okay. So let's just prove that part first, and then we will prove this proposition. So that brings me to so I'm not going to write down everything. We have a max flow instance, we have a flow, and we have a cut. Then the flow value is upper bounded by the capacity of the cut. Okay. Yeah. Let's say we prove proposition 3.3. Okay. Let's see why proposition 3.3 implies the corollary. So what is the left hand side? The flow value at for this, and that is exactly this quantity. What can we say about this? Exactly. So basically what we are doing is we are summing up for all the arcs, the x value for that arc, but by the capacity constraints, which we are going to use here, we know that each of them is less than equal to the capacity of that arc. And so the summation of all the x values is going to be less than equal to the summation of all the capacities. Right? So this quantity is less than equal to the sum of all the capacities. And this is because the x value is less than equal to c. Right? And what can we say about the thing we are subtracting? Non-negative, right? What we are subtracting is non-negative because the capacity constraints is 0 less than equal to x less than equal to c, right? So this quantity is greater than equal to 0 because 0 less than equal to x, right? We are summing a bunch of non-negative numbers, so the sum is going to be greater than equal to 0. And so therefore, this entire quantity is upper bounded by the capacity of the cut, which is exactly what we wanted to prove. Yeah. Okay. So what remains to prove is proposition 3.3. Yeah. So this is all right. Before we go there, let's look at one example from maybe yesterday. Yes, I'll have to switch the page. Yeah, okay. Can you see the other page I've shared? Thank you. All right, so let's go back to this example. And we want to focus only on the red colored numbers. We don't want to focus on the black numbers, okay? Because those are the capacities and they don't matter for proposition 3.3. And let me look at a particular cut that I have selected for the sake of illustration. Right. let's look at this cut here. So I'm going to pick a set of vertices that will contain the vertex S and will not contain the vertex T. Is this visible, this color, or should I change the color? It's okay. So what exactly is proposition 3.3 saying? It's saying that the flow value at the vertex S, which is exactly 2 plus 1, 3, is equal to the flow across this cut. So this is U and this is U bar. Outside the green line is U bar. So what is that quantity? So let's see what we have to do. We need to add up all the values of the arcs that are going from U to U bar, right? So they have the tail in U and the head in U bar. So let's see what that is. So this one has to be added. This one has to be added. This one here has to be added. And this one here has to be added. Okay, those are 4 arcs. There are 2 more arcs which are crossing this cut, but those are going inside U from U bar. So this one here has to be subtracted, and there is one more, right? This one here has to be subtracted. Those are going from U bar to U. Okay, so let's see what that is. We have got, what are we adding? We are adding 1 plus 4 plus 0 plus 2. And we are subtracting 1 and 1. Is that correct? Oh, it was not a 4. Sorry, my bad. I took the black colored number. This is a 1 plus 2 plus 0 plus 2. Yeah, sorry. This is not a 4. That was the black colored number. Yeah, good. All right. And this is exactly 5 minus 2, 3. Okay, so that is the content of this proposition. I hope everybody has a visual sense of what the proposition is saying. Are there any questions or concerns at this point before we prove this proposition? Anyone in the call? Is it clear what we are wanting to prove? Okay, hopefully that is a yes. All right, so let's go back to our original screen. Do you see the change? Okay, thank you. All right, so this is what we want to prove. Okay. So let's make sure we understand what this quantity is. So the right hand side is basically we are summing up for all the arcs in partial plus U, X, E values. I'm not writing a bracket generally, so let me just remove the brackets. And we are subtracting all the arcs in partial minus U, their XE values. Okay. And we want to show that this quantity is exactly equal to this quantity. All right. So how do you go about this? Any ideas? How do we compare the flow across the cut to the flow at the vertex S? Right. So you can think of this as flow at S, and we can think of this as flow across u bar. Let me just put it this way. The cut in the undirected sense. So it has to account for both kinds of edges. How do we compare these two quantities? Right. And we can say for every vertex where in U. Yeah, exactly. So it's similar to things like the handshaking lemma in graph theory. It's very similar idea. What we are going to do is we are going to add up the conservation constraints for all the vertices in U, right? Of course, the vertex S is also in U, so we should also take care of that somehow. So here is what we will do. So what do the conservation constraints tell us? Conservation tells us that for every vertex in the set U, except for S, the incoming flow is exactly equal to the outgoing flow. In other words, if you sum up the edges in partial plus V and their flows or X values, and you sum up the edges in partial minus V, their X values, this is exactly equal to 0. Yeah, that is the conservation constraint. On the other hand, we also have the vertex S, right? For the vertex S, we cannot say this. For the vertex S, we have that this quantity, so all the edges coming in at S and all the arcs going out. Sorry, I might be switching going it out and coming in, doesn't matter. So long as I'm writing the correct thing. This quantity is exactly how we defined the value of our flow, which is the left-hand side of the equation we are trying to prove. Okay. And this accounts for all the vertices in U, right? This is basically all vertices in U. So we have an equation for every single vertex. So what Revin is suggesting is that we look at these. What should we do now? Sorry? Add all of them, right? There's a bunch of constraints, one for each vertex in U. So we're going to add up all of these constraints. Right? So the plan is to add up all of these equations and see what we get. Okay. So on the right hand side, that's easy. We get the left hand side of what we are trying to establish. That's good. Now let's try to analyze this. Okay. So let me just write it down in the following way. For every vertex in the set U, including the vertex S, we are taking the edges that are outgoing from that vertex. Sorry, I did not mean U here, I mean V. And we are subtracting the edges that are incoming there. Okay, this is the left hand side. Does everybody agree? So far so good? Now how do we finish the proof? So we want to conclude that this quantity is exactly the right hand side of the equation we are trying to establish. How do we do this? I'm going to wait for someone else this time. Anyone in the call? Any thoughts? So right now we are thinking in terms of vertices, right? So this summation is in some sense in terms of the vertices. So for each vertex we are doing this. I want you to switch the way you are thinking about it. Instead of vertices, focus on the arcs. What happens to the arcs? What are the different kinds of arcs that are there, and how is each of them affected?
Every arc entirely within you will be cancelled.
Sorry?
Every arc entirely within you will be cancelled.
Right, exactly. Okay, so that is actually the summary. What he's saying is all arcs completely within you will be cancelled out. Okay, great. That is in fact the summary of what's going on. So there are three types of arcs, right? So one type of arc is those going out from U into U bar. Another type of arc is those coming from U bar into U. And the third type of arc that will be considered in this summation is arcs which have both ends in U. But these arcs will be added for one vertex and they will be subtracted for the other vertex in the summation. Right? Is that clear? So these third type of arcs will be completely cancelled out in the summation. The first type of arcs will survive because they are being added but they are never being subtracted. And the second type of arcs will survive in the sense that they will be subtracted but they will never be added. Right? So it is clear that this is exactly the left hand side of what we are trying to establish. Right? So essentially, switch viewpoint from vertex to arc and observe that arcs of type 3 are cancelled out. Right? This is type 3. And that is exactly the left hand side. Thus, take all the arcs going out and subtract all the arcs coming in. Okay? So that's it. That proves proposition 3.3. All right, and we have already seen how proposition 3.3 immediately implies the corollary because now we have the capacity constraints. So that is where they come into picture. But in 3.3, we did not use the capacity constraints anywhere, right? So in fact, I could have just said that we have a max flow instance which doesn't respect the capacity constraints, but rather than stating that, I just put it as a remark. Okay. So are there any questions or concerns regarding this upper bound that we have just established? So for any flow, its value is going to be upper bounded by the capacity of any cut. In particular, the value of a maximum flow is upper bounded by the capacity of a minimum cut. Right? Great. All right. And what is really cool is the MaxFlowMinCut theorem, which says that not only is it upper bounded, it is exactly equal to. All right. So that is what I want to just state. And I don't think I will have much more for today. So yeah. So theorem 3.5, which we will prove tomorrow, is the MaxFlowMinCut theorem. which says that if HSTC is any max flow instance and if X is any ST flow and partial plus of U is any ST die cut, then sorry, my bad, I'm writing the previous one. Then the value of a maximum flow is equal to the minimum capacity of any ST die cut. Okay. So this part is not entirely clear. The thing that we know is that this is less than equal to, right? So what we have proved so far is this part, but we haven't proved equality yet. Okay. Right. So this is due to Ford and Fulkerson. You might have seen the Ford-Fulkerson algorithm in some of your other courses, and also due to Kotzig, who did it independently, both in 1956. Kotzig did not write in English generally, so knowing what he had done was often a bit difficult, and it only came to light a few years later that he had also proved this. So largely it is called the Ford-Fulkerson theorem and the Ford-Fulkerson algorithm, but Kotzig also had this theorem proved independently. All right. Yeah, so technically we should say MaxFlowMin die cut, but of course in the literature it's just called MaxFlowMinCut. So we will see an algorithmic proof tomorrow. I don't know if we'll finish it. Mostly we will finish it. And I'm hoping that if time permits, we will also see a proof through LP duality, which is not algorithmic, but directly uses LP duality to establish the theorem. Right? If time permits, a proof via LP duality next week, which is also the last week of lectures. Maybe I'll just make a few comments regarding MaxFlowMinCut. So yeah, so I'm calling this module applications of duality and MinMax results, right? So this is one of the first MinMax results that we are seeing here. Turns out that using MaxFlowMinCut, you can prove a bunch of other MinMax results in combinatorics. Actually, there's a lot of applications of MaxFlowMinCut to get other theorems, which can all be formulated as flow problems, right? So I'll just state some applications since we have some extra time remaining. This is not an exhaustive list. I don't think I have the exhaustive list in my mind. So one of them is simply, so on the assignment 5, which I'm hoping to release this week, you'll be proving that in a bipartite graph, the cardinality of a maximum matching is equal to the cardinality of a minimum vertex cover. So that is the famous Koenig-Egervary theorem, often known as just Koenig's theorem. It says that for bipartite graphs, the max matching is equal to min vertex cover, right? And this can be proved using MaxFlowMinCut, but you will be proving on assignment 5 using um, using integrality of polyhedra that we have been discussing in the last few lectures. Okay. All right, but there is another way to do it, which is through MaxFlowMinCut. All right, you can also generalize it to matchings with costs, but I'm not going to state that generalization. It's generally called the generalized Koenig's theorem, but I won't state it. If you have taken a course in graph theory, you would have seen Mengers theorem or multiple Mengers theorems. So in Mengers theorem, what you're trying to do is you're trying to find lots of paths between two vertices, right? Either in a directed setting or in an undirected setting. And what it says is that the maximum number of disjoint paths where disjoint needs to be clarified is exactly equal to the size of the minimum cut. And again, which cut you are referring to depends on what definition of disjoint you are using, right? So you can say vertex disjoint paths, or you can say edge disjoint paths, or you can say arc disjoint paths, blah, 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 right? So there are lots of different Mengers theorems, and all of these can be proved as applications of MaxFlowMinCut. Right? So essentially what it says is that the maximum number of disjoint, depending on the definition you are using, paths is equal to the cardinality of a minimum cut, where the cut definition depends on the disjoint definition. Okay. So if you haven't seen Menger's theorem, you can take a look at my other courses on YouTube, and I talk about them in both in structural graph theory and in advanced graph algorithms. What else? Are there any other theorems? There is a theorem called Gilberts Theorem, which is about partially ordered sets. You can read about it. So you are looking for, instead of looking for paths in a graph, you have a poset. Is everybody familiar with the poset, partially ordered set? Okay, so you have a poset, and you're looking for the maximum number of chains in the poset, and that is upper bounded by I think the concept in poset theory is called anti-chain or something. I'm not sure exactly. Anyways, so I don't remember the exact phrasing of Dilbert's theorem, but turns out you can also prove it using MaxFlowMinCut. It's about posets. Okay. What else? Anyone knows about any other applications? Am I missing any applications? I want to mention one cool thing. There is also a min-max result for non-bipartite graphs. So it's not, maximum matching is not equal to minimum vertex cover for general non-bipartite graphs. But there is a min-max result, which I'm not sure if we will have the time for it. But that one is not implied by MaxFlowMinCut. At least so far, we don't know if you can prove that result using MaxFlowMinCut. So an example of a result which is not known to be provable using MaxFlowMinCut. It basically is called the Tut-Berge formula. And what it does is it relates the size of a maximum matching in any graph. Right? So it's a min-max result. You're relating the maximum size of any matching to the minimum of a certain quantity. Okay, I won't state this quantity right now. In the interest of time, I'll probably do a better job of it later if we have time. Maybe in the last lecture we'll talk about it, right? So it's you can think of it as a generalization of Koenig-Gilberts theorem, but the right concept to look at is not a vertex cover. It's a different thing that we want to be looking at. And if you consider that combinatorial or graph theoretical concept, then you get a similar min-max result for all graphs for maximum matching. Okay, so I'll just state that we will discuss this later. Okay, so that is one of the reasons why all of matching theory is not subsumed by flows and cuts. For bipartite graphs, most of the things you can do using flows and cuts. But for non-bipartite graphs, you actually need new ideas because they are not captured by MaxFlowMinCut results, which is why Jack Edmonds and Bill Tutt and others had to come in to rescue humanity, right? At least the combinatorialists. Okay. Yeah. Are there any questions or concerns? Yeah. So yeah, so that's all about MaxFlowMinCut applications and limitations, right? So this one can be viewed as a limitation of MaxFlowMinCut. And that is why in combinatorial optimization courses, you generally talk about non-bipartite matchings quite a bit because you can't do it using MaxFlowMinCut. Yeah. All right. So that's all for today. And yeah, if there are any questions or concerns, please ask them. Anyone in the call? All right. If not, feel free to leave the meeting and I'll stop recording.